we're going to look at patterns in the atomic table. And this is where the strength comes. There's a lot of stuff on that table, but there really is only a small amount that you have to learn because it's structured by repetitive properties. In other words, if you learn about one element, you wind up learning about 8 in total. And that simplicity makes it very easy to understand. I've created this table at great expense. More than 20 members of my family died in the creation of this table. I worked very hard on it. Learn to use it. Okay? Get tired of people going, yeah, there's some really tiny print in there, but you can zoom in. You got young eyes. This table is divided into some basic zones. Notice I got rid of the atomic mass because you don't need it till we get into radiation. If you've done your work correctly, you would have noticed that hydrogen, beryllium, boron, carbon, nitrogen, oxygen, and fluorine have these Lewis dots. The last column I didn't put here because they're full. They're full of it. They're noble gases. They're totally full of it. They're not going to participate in chemistry. Hydrogen appears on both sides of the table. We'll get to that later. The pattern you are learning fails to operate in here, called the transition metals, and you will look it up directly. So in your textbook, it will say +2 or +3, which you can interpret as iron as being this or iron as being that. And I will tell you when you need to know that. Everything in this column here is going to look like hydrogen's Lewis dot, not the Bohr diagram. That is unique to every element. Everything in hydrogen's column will have a single electron in the valence shell. Everything in beryllium's column will have 2 electrons in the valence shell. 3, 4, 5 electrons in the valence shell. 3 are missing. 6 electrons in the valence shell. 2 are missing. 7. And then a full shell. This means if you know what hydrogen does, that will apply to all the others down below it. If you know beryllium, you'll know all the ones below it. And that works in this column and in this column. And it works in this column till you hit this little black staircase. And then see, pattern fails in here. Read valence table directly. These outer 4 columns are so important they've been given names. In actual fact, all the columns got named, but nobody cares anymore about these outer 4. And yes, you have to know their names. Look at the bottom of the screen. Alkali metals, alkali earths, halogens, and noble gases or inert gases. Okay? This is the summary of everything you need to know for grade 9 and 10 on this. Elements that are alkali metals have a single valence electron in their outer orbit or shell. The alkali earth metals have 2. The halogens over here are 1 from perfection. These little guys got 1 pesky electron in their outer shell, blocking them from being perfect, clean atoms like neon. Beryllium has 2 pesky electrons in its outer shell that's preventing it from looking like this. And fluorine just needs 1 more little electron and it would fit in with the nobles. They'd be like, by Jove, it's you! Well, why don't you join us now? Oh my God, he's not a nobleman at all! That's a stolen electron! Police! Alright? No. So, these guys are perfect. So read this. Now, hydrogen, yeah, it's on both sides. Why? Because hydrogen could choose to pick up an electron and finish its valence shell, or it's actually willing to throw away its only electron and go out buck naked, a completely nude proton showing its bare nucleus. It's the only element that can do that. So my table has hydrogen on both sides. Other textbooks might just say +1/-1. Hydrogen's a weirdo. Okay? Now, when we name compounds, most of them start by naming the metal on the left, followed by the non-metal on the right. You probably think sodium chloride sounds perfectly reasonable. You've never heard of chlorine sodide. So the naming scheme tends to favor left followed by right, and emies turn to ides. No one says, can I have some sodium chlorine? You go, no, sodium chloride. So you, in fact, have already absorbed some of the naming scheme in your life. What we want to do is look at the behavior of these 4 columns, and you should be able to describe just the 4 columns what's a consistent behavior with them. So alkali metals all have a single valence electron. This makes their behavior all very similar. They wish to give away that one valence electron to expose the full shell below, or if you're a streaker like hydrogen, you'll give away that single electron and run around with your butt-naked proton sticking out. If you give away or accept an electron and you become charged, you get to be called an ion. And you must learn that term. Let's take lithium. It has 3 protons and 3 electrons. See? A 1, a 2, a 3. And 3 in the middle. And the neutrons are just hanging around doing nothing. Like those guys at a bait shop. You ever go to one of those old hardware stores? There's one guy working and 6 of the old guys just hanging around doing nothing. So the neutrons are just hanging out. So lithium looks like this. 3 pluses and 3 minuses. If you take away one of these electrons, if I scratch this off, you're adding up +1, +1, +1, -1, -1. You're left with a positive charge, and it is now a positive ion. When it does that, it has perfected its shell by erasing this outer one and exposing the complete shell down below. All of them do this. Now, where do these things come in usefully for us? Well, hydrogen is a flammable gas, and it's 75% of the whole universe and something like 75% of your farts. And yes, your farts do ignite. Why do you want to get known for that? They will donate their outer electron, and they will do so violently. Now, the part that puzzles us is that all of these are metals with the exception of hydrogen. If I go backwards here, hydrogen is the only gas on this side of the table. And they don't know why hydrogen is a gas. And they've tried to see if they can make a metal version of hydrogen. Lithium, sodium, and potassium are metals that if you chuck them into water, they explode. And we're not at school to see that, so I'll show you some internet videos. Lithium, you may have heard, you've got lithium batteries. It's a super important strategic metal. Sodium chloride is table salt. Potassium chloride is a salt found in bananas. It's a good salt. It lowers your blood pressure. Sodium chloride raises it. Rubidium, cesium, and francium are really of not much concern in your life. They can be radioactive. They're highly toxic. Francium is so rare, it has never been studied except in microscopic amounts. They figure it's so unstable that if you put together a piece not much bigger than a chewing gum chiclet, that it would explode on its own. So nobody on planet Earth has ever held francium. One equation we're going to learn is what happens when you set fire to hydrogen. Hydrogen plus oxygen make water. And you're going to learn why the formula can only be this way. I've isolated 3 of these. All of them have the same Lewis dot diagram, but they do not have the same Bohr diagram. So if you were to interact with them, sodium will actually lose its electron even quicker than hydrogen would. Because, got to remember, the protons in the nucleus would prefer that it stays, but the rule is these shells should be perfect. So if you consider these nucleuses to be electron farmers, you could pop off this electron on rubidium and the farmer in the middle would hardly ever notice. If you pop the electron off the sodium, it might go, oh, whoa, wait a minute. But if you go to grab the electron off hydrogen, they're going to notice right away. And I've just noticed, curses, I've still got a flaw in this. Look at that. I've got the wrong nucleus for them all. I've still got fluorine's nucleus there. This is what I mean. There's no such thing as fixing anything. And that's not my breathing. It's my cat. She wants attention. So she is like interfering actively with this lesson. Here, she's trying to pass me some electrons. Okay, so we're going to learn about these, but I must fix that nucleus. All right. Now, if you were attacking castles and you were outside this castle, you'd go like, dude, there's only one guy in this wall. Same with that castle. Same with that castle. Well, I guess it doesn't matter who we attack. Yeah, Jim, you take this castle. Biff, you take this castle. And Nebuchadnezzar, you take this castle. And this guy's going to like, you screwed me. I killed the guy on the outer wall, and I found all these guys inside. So while the behavior is remarkably similar, it will change. Technically, they get a bit more aggressive, nasty, as you go down the table, but not always. Lithium has become kind of important. Look at this. In 1920, it was just a scientific curiosity. By the 1960s, people started coming up with uses for them. And now, if your lithium in this world disappeared, say goodbye to cell phones, laptops, and a lot of other devices that we need lithium. And lithium is becoming a very valuable commodity. I've owned some lithium stocks, and I made not much, like just a small amount of money, like $1,000, and I made a little bit and lost a little bit. Canada has no ability to produce lithium, neither does the United States much. The bulk of the lithium on planet Earth is in China, and so we need to invest in lithium mines in Canada because we are dependent on getting along with the Chinese. I'm not recommending not getting along with them, but this is a highly strategic metal. Not only where your cell phones work, batteries in jet aircraft are made out of lithium. So the fact that we cannot make our own lithium and have to buy it all from China, that is what's called a strategic problem. Because if we ever angered the Chinese and they decided, that's it, no lithium for you, we're done for. And they have the world's largest population and they want cell phones and a nice living too. So if we don't solve this issue, in a few years, cell phones might double in price. Unfortunately, as great as lithium is for our uses, mining it is kind of terrible for the environment. And there might be a project in here for some of you. If we move on from lithium to alkali earth metals, the most familiar one to you is probably calcium. And for reasons that are pretty obvious, most people think calcium is some sort of milky white powder because it's in milk. Well, calcium is a metal. And if I gave you a piece of calcium and said, here, it's good for your bones, chew it, it would blow your teeth out of your face. You would like die screaming and like foaming at the mouth as the calcium destroyed you. You cannot eat pure calcium. It would be a horrible death if you put it in your mouth. What you wind up eating is like calcium carbonate, which is similar to chalk, or calcium chloride, which is not calcium chloride, it'd kind of burn too. But the calcium in your bones is needed. Now, the weird thing is, if you need one element on the table in your diet, there's good odds, not perfect, that you might need the ones above it and below it as well. So, yep, your body needs magnesium and strontium. If you go to the store and you try to buy calcium supplements, you will not be able to find a box of calcium pills. They will say calcium with magnesium. They have to blend the two. If you just take calcium only and you eat too much calcium supplements, your body will run out of magnesium because the docking bays in your body can't tell magnesium apart from calcium. So if you take an excess of calcium and don't eat enough magnesium, your body will go like, oh, we're full, we're done, and then ignore any magnesium that comes in. So these treating yourself for vitamin deficiencies in the store is a bad move. You must buy a blended CalMag mix, they call it. Alkali earth metals are somewhat familiar to you. Magnesium and calcium most people have heard of. Magnesium is frequently used in flares. Once ignited, it's very difficult to put out, and it has a very simple combustion formula. Magnesium plus oxygen makes magnesium oxide, and you're going to be able to put this equation together in the next day or so. Beryllium is one I'd like to spend a bit more time on because it's very important in our world, and most of you probably haven't heard of it, yet you encounter it almost every day. Beryllium is present in your world all over the place, but there are some highly noteworthy uses of it. One of them is beryllium copper alloy tools. And yes, there is a beryllium company. So you can see this is not a chemical formula because an alloy is not a compound. They're not bonded. If you melt this down again, you could skim off the beryllium if its density is different from copper. But here are some beryllium alloy tools. Now, why would you want such a tool? Copper is non-sparking, but a copper tool is soft. Add beryllium, you can boost the strength by 7 or 8 times. So you've got a tool that's not sparking, it's non-magnetic, it's resistant to acids, and it doesn't become brittle at cryogenic temperatures like in liquid helium. So it makes it very desirable for those kinds of uses. The non-magnetic properties are great if you're doing looking for things with magnetism. If you've got a magnetometer and it's made out of a magnetic metal, it's going to keep detecting itself. The trade-off, it's not as strong as steel, but what if you're trying to diffuse an old World War II mine that's magnetic? You'll set it off. These tools are used in hazardous environments. A gas fitter might have them because he doesn't want to create a spark when he's working with flammable gases. In the military, a lot of the equipment is made out of brass or beryllium alloy if you're diffusing what could be a magnetic mine or anything that has a magnetic detection system. The trade-off is the cost. A $3 wrench at current 2020 prices is $150 out of beryllium. These little wrenches here that you could buy for $60 or $70 at Home Depot are over $500 a piece. In a more extreme example, I got to meet Canada's unexploded mine team, and their equipment is completely non-magnetic, non-electrical. And they had little scuba tanks, not much bigger than a big melon. And they were made out of beryllium alloy. And those tanks were $8,000 each. And that was 20 years ago, when a scuba tank would be about $150. These are the valve lifters in a car that's using beryllium alloy. And this is where air goes in and out of the engine. They have certain thermal properties that make them very desirable, but they've been banned in the Formula One racing for a combination of 2 reasons. Unfair advantage to one team, and there's worry that under the aggressive driving conditions that these engines are often failing, right? They're pushing them right to the edge. They're worried about toxic dust from the beryllium. The single largest piece of beryllium ever manufactured was the heat shield on the Mercury, Gemini, and Apollo spacecraft, a pure shield of beryllium, and the company that makes it is still around. The beryllium has a high melting point, but it also absorbs heat really well and carries it off. They've switched materials over time, but the beryllium was still a really good heat shield, just expensive. You know, if one of those wrenches was $500, try to imagine this shield of pure beryllium, how expensive it was. Currently, beryllium is being favored in a lot of mirrors, and this is the James Webb Space Telescope, and the mirrors are made out of beryllium. Everything to the left of this line is essentially metallic, except for hydrogen, which is the only metal to the left of this staircase. To the right of it, we have nonmetals, and in fact, a good portion of these are gases. The ones that are tucked close to the line itself straddle the boundary between a metal and a nonmetal. Aluminum is definitely a metal, but it's not like a lot of other metals. It's not particularly shiny. It doesn't actually even rust in the way we normally see rust. It's bendable to a point, but will break. Silicon, which is in solar cells, looks like a metal. It feels cool to the touch like you'd expect a metal, but it's dark. It's very dark in color, and if you go to bend it, it'll bend for a bit and then snap like a cracker. Carbon is definitely not a metal, but it conducts electricity in a certain direction almost as good as a metal. We see that this transition is not super sharp, So the ones tucked along the line are called metalloids, and the primary ones in your world, silicon, germanium, they are in a lot of our electronics. Same with arsenic, selenium. That's these two outer columns. Here, and this one. This column is called the noble gases because it does nothing at all. These ones are called the halogens. And the oxygen column is called chalcogens, but no one's going to use that term anymore. Missing 2, missing 1, perfect. You need to know the names of these two columns and a rough description of their behavior. The oxygen family, the name chalcogens is not testable, are all characterized by a valence shell that's just missing 2. So they will pick up 2 to become complete. They're all nonmetals. Oxygen supports fire and is very reactive. The ones below it are reactive as well. Sulfur is not gaseous. Selenium is getting very metal-like. And tellurium is basically a metal, even though it's on the right side of this line. And it's an unusual metal because it's one of the only ones that actually has an odor. Tellurium, like most heavy metals, is quite toxic to us. And if you work with tellurium dust in a lab, one of the signs that you've poisoned yourself with tellurium is you get what is known as tellurium breath. You actually get like a garlicky odor to your breath, which indicates you've managed to ingest a fair amount of tellurium. And polonium is definitely a metal. It's highly radioactive and highly toxic. And if you go through your textbook, you will find a Russian man who was poisoned, possibly by Putin, poisoned by Putin with polonium. One of my favorite elements is sulfur. And it's unfortunate, I had some really cool demonstrations to show you about sulfur in the classroom. And it's the one demo I've never succeeded in recording because I have to make a rig to hold everything to show it. This is Jupiter's moon Io, and it's completely covered in sulfur. And you can see sulfur volcanoes ejecting here. This is on the island of Indonesia, where there is an open pit sulfur mine where people risk their lives, destroy their health, working in basically Io on Earth, collecting sulfur without proper respiratory protection. And they wind up dying very young as a result of this job. And I have a video separately on that. Now what's interesting is carbon can form pencil lead, charcoal, and diamond. Sulfur can do something similar, and that was going to be my demo for you. And what you see here is all basically pure sulfur. The element can take on many different forms similar to diamond and carbon. And the forms have different colors, but they're not particularly stable, so given time they'll turn back to what they were. The fluorine family is called the halogens, which means salt making, and they're characterized by one missing valence electron. So as you get closer to full, you go from 2 missing to 1 missing, they tend to get more aggressive because he just needs that 1 to complete himself. If you start at the left side of the table and count, fluorine is 7 places over. 7 places over, 1 to go. They're all dangerously reactive. Fluorine you don't hear of as much. Hydrochloric acid is in your stomach. But you can clean your pool with chlorine, bromine, and iodine at that point becomes a solid, and it can be used to sterilize cuts. Astatine, similar to francium, is so rare nobody's ever seen it. It is the rarest element in the universe. They estimate there's no more than a gram or 2 in all of planet Earth. We know its properties because it has the same structure as these guys, so it's going to behave very similarly. And we know where to put it on the table, even though we've never experimented with it in the lab. The noble gases on the far right have no participation in chemistry. They have no net charge. They come with complete valence shells, so they are essentially perfect. And the end result is they will not react with other elements to complete their valence shells. So they were given the name noble gases or today inert. But they're like pompous, like, no, I didn't want to play with you. I am perfect the way I came. The textbooks will say they have a complete octet. I've never liked that phrase because helium is complete at 2. But the others all have an outer shell with 8 electrons in place. Goldmember says neon is a noble gas. It has no vacancies. Neon is used in hotel signs that say no vacancies. Isn't that weird? Unlike real nobles, noble gases actually have uses. All of them can be used in lasers, as insulators, as shielding gases. They can be used in deep-sea breathing mixes. Some of them have a slightly more particular use. Helium is very important in our MRI machines and nuclear reactors. So much so that you are probably going to see the banning of helium balloons in your lifetime because we don't have enough to go around. The United States is running out of helium and they're the world's producer. And if we run out of helium because we're filling our birthday balloons, we can't run our MRI machines. Neon is used in lights and lasers. The helium neon laser is one of the most common laser out there until the laser diode came out. And the laser diode is the one that allows you to have little pocket pointy lasers. Argon is a great insulating and a shielding gas. It insulates against heat fairly well, so good quality windows in a home are argon gas sealed. They put a little layer of argon in there and it helps the glass be a bit more insulating. It's insulating enough that real deep sea divers that are in dry suits sometimes use argon in the suit to help keep them just that little bit warmer. In welding class, you blow argon across the weld joint as you're working to keep oxygen away from it. Oxygen, if it meets the arc, will cause the metal you're operating on to quickly oxidize and you'll get all this black crumbly crud that ruins the weld joint. Xenon and krypton you are most familiar with in your camera flashes. Krypton is not kryptonite. The word crypt comes from hidden, like burying a person in their crypt. Cryptography means hidden meaning in writing. So krypton was defeating the scientists who were trying to find it, so they named it hidden. Xenon is increasing in its uses because it turns out it acts like a tranquilizer in people and can be used as an anesthetic in surgery. Radon is a byproduct of radium decaying and other radioactive decay in the earth, and it's a radioactive gas. It's a health hazard. It has scientific uses, but you really don't want to encounter it. Since it's a natural product of radioactive decay, it can accumulate in a house under specific conditions. And the typical conditions to get radon in your home is you have an old home that's been sealed up tight. So you buy yourself a 100-year-old home, you re-insulate, you tape up all the seals, you put in good sealed windows, and you bring the home up to a really tight modern standard, except the basement is a dirt floor. It's just a crawl space or a small space for the furnace, and the dirt floor now lets radon in, and the house is no longer leaky, and so the radon accumulates. So it's important to have an intact cement floor in a house. All of these gases have been experimented with in deep sea diving mixes because nitrogen becomes toxic under pressure. You can't switch to pure oxygen or that will kill you. So as divers go deep, they start adding helium is the main gas. Other times they'll add neon, argon. They've experimented with different gases to change the breathing mix. So unlike the movies, once a diver's down really deep doing something hardcore, he has helium voice. So he sounds like Donald Duck diffusing the mine. You can see why movies skip that. In fact, under pressure, many divers, the helium breathing mix will send their voice so high they become inaudible to other human beings, and they need a conversion mouthpiece to re-lower the sound of their voice so it can be heard. Chlorine and its compounds were first put to use as bleach to create truly white clothing. Semmelweis was a doctor who was able to create the first bleach soap in 1847 that lowered the patient infection rate up to 90%. Our modern water treatment and swimming pools are possible with chlorine disinfectants, but it was also sprayed onto the battlefields of World War I and quickly replaced by more deadly chlorine compounds, mustard gas and phosgene. In World War II, American troops were accidentally poisoned by their own stockpile of mustard gas. A new effect was discovered. It killed bone marrow. A doctor tried it on patients with leukemia, which is bone cancer, and it was able to destroy the cancer. Chemotherapy was born. Today, we still inject cancer patients with the same deadly chemical used in World War I to kill the foreign enemy, except now it targets the enemy within. These elements are not inherently good or bad, it's our use of them. You'll study leukemia and chemotherapy in grade 10, and that will be a link to this assignment. Something that is always skipped in movies, if you went to the past, prior to the 1700s, you would have seen the hills covered in white cloth. The only way they could make white was to lay it out in the sun and have these giant bleach fields spread out on the hillsides. So that would be something you wouldn't think you'd see. You can imagine how labor intensive that was. So if you could go back in time with a white shirt, you'd freak people out. They'd be like, how did you get that color? This is not the first generation of people that feel they had to go outside covering their faces. These early gas masks were completely ineffective. They usually peed on them, and that pee would react with phosgene and reduce it a bit. You see these guys letting fly? They've got no protection. So here the poor Germans that are opening these canisters are standing there without anything to protect themselves. Poor Semmelweis, when he made the disinfectant soap, doctors were so against hand washing, even though he was proven that he could lower the rate by 90%, he was still driven away because the doctors didn't like all his quarantines about don't travel from one ward to another, never bring anything from one ward to another, wash your hands between every set of patients. And they fought him tooth and nail on it until eventually he went crazy. He was beaten in the asylum because that was a standard treatment for insanity, and he died of an infected wound that probably could have been treated with his soap.